Hello everyone, welcome to my presentation. My name is Diksha and along with my friend Tanvi, I'll be presenting our embedded systems project on microwave oven stimulation using PIC microcontroller. This project is developed as a part of our internship at Emertxe, where the main focus is on embedded C programming, microcontroller interfacing, and a real-time system behavior. In this video, we will explain both the uh, theoretical concepts and the practical implementation in detail. Moving on to the next slide. Before starting, let me give you an overview of what we are going to cover in this presentation. We will begin with a basic introduction of microwave oven, followed by the project overview. Then we will discuss the requirements, C programming basics, embedded systems, PIC microcontroller, display, keypad, timers, interrupts. These are basically the components used in our project. Then the project architecture and stimulation using PICSimLab. By the end of this video, we will clearly understand how a real microwave oven works internally using embedded concepts. Now let us get an overview about a microwave and how it works. A microwave oven is an electronic cooking appliance that uses microwave frequency electromagnetic waves to heat food. These microwaves typically operate at 2.45 GHz frequency. At this frequency, polar molecules like water present in food starts vibrating rapidly. This vibration creates heat internally, which cooks the food. Unlike conventional ovens, which heats food from the outside using conduction ovens heat food from inside, making cooking faster and more efficient. The applications of microwave oven, they are widely used in homes for quick cooking, in restaurants for fast food preparations, laboratories for heating samples, food industries for mass processing. Then the main advantages are its speed, energy efficiency, and the ease to use. Due to these advantages, microwave ovens have become an essential household appliance. Now, coming to our project. This project stimulates the basic functionality of microwave oven using a PIC microcontroller. The main aim is to cook the food physically, but to replicate the control logic of microwave oven, of a setting time, selecting mode, starting, pausing, and stopping the operation. This project helps us understand real-time embedded system behavior. Now, let us understand the modes of microwave oven. In our project, we have implemented three operating modes, just like a real microwave oven. Micro mode, conventional mode, and grill mode. Now let us understand what these mode represents. So micro mode is basically the normal heating mode. Then conventional mode is the baking style heating, and the grill mode is surface heating. Each mode has different time and behavior settings, which are controlled using keypad inputs and displayed on the LCD. Let us now discuss the hardware requirements and the software requirements. So, in hardware requirements, we use PIC16F877A microcontroller as the core controller, CLCD display to show time, mode, and status, then matrix keypad for user input, buzzer for alert after cooking completion. All these components together form the complete embedded system controller. Then the software requirements. For software, we use MPLAB IDE for writing and debugging the code. Then XC8 compiler for compiling embedded C code. PICSimLab for stimulation and testing. PICSimLab helps us test the project without real hardware, making debugging easier. So now let us see each and every part in detail of software and hardware and what we have learned in software and hardware. So in software, next basic of C. C is generally a general purpose procedural programming language developed by Dennis Ritchie in the year 1972 at Bell's Laboratories. C language is very close to hardware, which makes it extremely suitable for system level and embedded programming. It provides a perfect balance between high level language features and low level hardware control, which is why C is widely used in embedded systems, operating systems, device drivers, and microcontroller programming. Then let us understand that why C is used in embedded systems. C language is preferred in embedded systems because it is fast and efficient. It uses less memory and it allows direct hardware accessing using pointers. Also, it produces a compact machine code. In embedded systems, resources like RAM, ROM, and power are limited, and C language helps us optimize these resources efficiently. Now, let us understand the basic structure of C programming in detail. So, the documentation section, it helps in providing the comments and explaining the program. Then the pre-processing directives, it includes the hash include, hash define, such statements. Global declaration is the declaring the variables and functions globally. Then the main function, these the program execution starts here. Then the function definition, it is a user-defined function where the user defines the functions. This structure makes the program modular, readable, and reusable, which is essential in embedded applications. Now, let us see variables in C. A variable is named memory location used to store data. For example, int time is equals to 30, char mode is equals to m, or we can take a is equals to 3. A is a variable here and 3 is a value assigned to a variable or the data stored in variable A. In embedded system, variables are used to store sensor values, timer counts, user inputs, and system states. Now, let us see data types in C in very detail. Data types. What type of data a variable can store? How much memory is allocated? What operation can be performed? Choosing the correct data type is very important in embedded system because memory is limited. So classification of data types in C. C language data types are mainly classified into basic data type, derived data type, user defined data type, and void data type. Basic data type int. Int is used to store integer values. In microcontroller, int is commonly used for counters, loop variables, timer values. Then the second is char. Char is used to store the single characters. It occupies 1 byte of memory. In embedded system, char is widely used because it consumes less memory. Then the next is float. Float is used to store decimal numbers. Floating point operations are slow in microcontroller, so they are used only when necessary. Double. Double stores double precision floating point values. It consumes more memory and is rarely used in embedded systems. Then the next is derived types, derived data types. That is arrays. An array is a collection of same types of elements stored in continuous memory location. Arrays are used in embedded systems for keypad scanning, display buffers. Next is pointers. A pointer stores the address of another variable. Pointers are extremely important in embedded systems because they allow direct hardware register access, efficient memory usage. Then next is the user-defined data types. Structures. Structures allows grouping of different data types. Structure improves code organization. The next is union. Union allows different variables to share the same memory location, used when memory optimization is required. Enumeration, that is enum. It is used to define named constant values. This improves code reliability. Then the void data type. Void means no value, used in functions that return nothing. Generic pointers. Now, this is all about C. Now let us understand about the embedded system in detail. An embedded system is a combination of hardware and software designed to perform a specific task. It works within real-time constraints and is optimized for performance, power, and cost. The characteristics of embedded systems are: it is dedicated to function, it provides real-time operation, also uses low power and is small in size and has high reliability, which makes it advantageous and better characteristics performance. Now, the components of embedded systems are microcontroller or microprocessor, memory, RAM, ROM, flash, then input devices such as keypad, sensors, output devices like LCD, buzzers, and power supply. Now, let us see types of embedded system. Embedded systems are classified into standalone system. Now, in our project, we are using standalone systems, then real-time systems, network systems, mobile embedded systems. Real-time embedded systems. In real-time embedded systems, correct output must be produced within a given time. Microwave ovens are hard real-time systems because delay can affect safety. Role of embedded in C. Role of embedded C. Embedded C is an extension of C language that includes hardware-specific libraries, register-level programming. It allows direct control of microcontroller peripherals. Let us see the development flow. Embedded system development includes requirement analysis, hardware design, software development, simulation and testing, and development. Now, taking an embedded system, like taking microwave oven as an example for embedded system. A microwave oven is a classic embedded system where keypad acts as input, microcontroller processes logic, LCD shows output, and buzzer provides alert. All operations happen in real time. Understanding C language and embedded system is essential for designing reliable real-world applications. This project will help us apply both theoretical concepts. Now, moving on to the project part, and let us understand the components in detail. A microcontroller is a compact integrated circuit designed to perform a specific control-oriented task in an embedded system. It can be considered a complete mini computer or a single chip, as it contains a central processing unit, memory, and input-output peripheral, all integrated together. Unlike general-purpose computers, microcontrollers are not designed to perform multiple tasks. Instead, they are optimized to perform one dedicated function continuously, efficiently, and reliably. Because of their small size, low power consumption, and cost effectiveness, controllers are widely used in embedded applications such as microwave ovens, washing machines, automobiles, medical devices, industrial automations, IoTs, etc. The CPU is the core of the microcontroller and is responsible for executing program instructions. It performs arithmetic and logical operations, controls data flow, and manages communication between different internal blocks. The CPU operates using a fetch, decode, and execute cycle, where it continuously fetches instructions from the program memory, decodes them, and executes the required operation. The speed of execution depends on the system clock frequency, which provides timing synchronization for all internal operations of the microcontroller. Microcontrollers also include timers and counters, which are essential peripherals for time-based operations. Timers are used to generate delays. It measures time intervals and schedule tasks, while counters are used to count external events. In real-time applications, like a microwave oven, timer plays a crucial role in controlling cooking time, generating buzzer alerts, and managing different operation modes. Timers operate based on internal and external clock signals of the microcontroller. The clock system provides the timing reference of the microcontroller and determines the speed of instruction execution. Microcontrollers can use either internal oscillator or external crystal oscillators depending on accuracy and performance requirements. Along with this, microcontroller also offers power management features such as sleep and idle modes, which helps reduce power consumption. Microcontrollers are typically programmed using C or assembly language, and the compiled program is loaded into the microcontroller's program memory using the programmer or debugging tool. The applications, like it is used in applications like microwave oven. The microcontroller acts as a central control unit, continuously monitoring inputs and processing the logic, controlling the outputs, and ensuring real-time operation. Thus, microcontroller forms the heart of any embedded system, enabling intelligent control and automation of real-world devices. Now, let us understand what is a microprocessor and then differentiate the microprocessor and microcontroller. A microprocessor is an integrated circuit that functions as a central processing unit of a computer system. It is responsible for performing arithmetic operations, logical decisions, instruction decoding, and overall control of the system operations. Unlike a microcontroller, a microprocessor does not contain internal memory or input-output peripherals. Instead, it requires external components such as RAM, ROM, storage devices, and input-output interfaces for functioning properly. Because of this, microprocessor-based systems are generally larger in size, consume more power, and are more complex in design. Since a microprocessor does not include internal memory, it relies on external RAM for temporary data storage and external ROM on storage device for storing program instructions. This external memory architecture allows microprocessors to handle large programs and large data sets, making them suitable for applications that requires high processing power. However, this also increases system cost, power consumption, and hardware complexity. One of the key strengths of microprocessors is their ability to run general purpose operations or such as like general purpose operating systems such as Windows, Linux. These operating system enables multitasking. They are designed to handle a wide range of tasks rather than a single dedicated function. Microprocessors are typically programmed using high-level programming language such as C, C++, Python, Java, often with the support of operating systems and software frameworks. Now you will understand why we have learned so in such a deep about microcontroller, because we are using the PIC microcontroller for controlling our all the input outputs of the microwave oven. PIC microcontroller, where the PIC stands for Peripheral Interface Controller. It is a family of microcontroller developed by Microchip technology. They are widely used in embedded systems due to their simple architecture, low power consumption, and ease of programming. They are especially popular in educational and industrial commercial embedded applications. They are designed to perform dedicated control tasks by executing instructions stored in the internal memory and controlling connected peripherals in real time. It integrates all the essential components of computer system on a single chip. It also includes the CPU, program memory, data memory, input output, then the communication peripherals as well. The CPU executes instructions using fetch, decode, and executes as we earlier discussed about it, ensuring continuous operations as long as power is supplied. They uses reduced instruction set computer, that is RISC architecture, which allows faster execution and simpler instruction decoding compared to complex instruction sets. Most instruction executes in a single clock cycle, making the system efficient and predictable for real-time applications. They provide multiple input-output ports, which allows interfacing with external devices such as keypads, LCD displays, LEDs, motors, and buzzers. These are all the components which we are already using in our program and interfacing all them at the same time, which is already an application of PIC or a feature of PIC microcontroller. Each input-output pin can be configured as an input or output using a specific control register. These pins are capable of performing alternate functions such as analog input, serial communication, or timer input, depending upon the configuration. It is flexibility. It is flexible, and this makes suitable for a wide range of embedded applications. PIC microcontroller includes built-in communication interfaces such as UART. Another important feature of PIC is low power consumption and power management modes such as sleep mode and idle modes. These features make PIC microcontrollers ideal for battery powered and energy efficient embedded systems. They are basically programmed in embedded C or assembly language, typically using development tools like MPLAB IDE and X8 compiler, which we are already using currently in our project. Once programmed, the code is flashed into the microcontroller's memory using a programmer or a debugging tool. Now we will understand these processes in detail by seeing the simulation of our project. Now the project architecture will be explained by my colleague Tanvi.
Now, I will explain the project architecture of microwave oven system. This slide gives the complete overview of how the different hardware and software components are connected together to form this system. The main goal of this project is to simulate the working of the real microwave oven using a PIC microcontroller, keypad inputs, then display output, and alert mechanism. So, let's talk about the main functional unit: input unit, processing unit, output unit, and alarm unit. Each unit has a different defined role. The PIC microcontroller acts as a central controller, coordinating communication between all these units. This architecture makes the system easy to understand, reliable, and scalable. Then let's talk about input unit. So input unit is implemented using matrix keypad. This keypad is a primary way through which the user interacts with the microwave system. Using keypad, we can select different operating modes, set the cooking time, then start, pause, or resume the operation. Each key on the keypad is assigned a unique key value. We will see that in our simulation part. So internally, these key values are mapped to a different function using if-else operation, then flags in embedded C program. So let's talk about one example. So here we have assigned one key to select microwave mode, then second for grill mode, then third for convection mode, and similarly for uh, start mode. So then let's talk about processing unit. The processing unit is the heart of the system. So the PIC microcontroller continuously monitors the keypad input and processes the user's selection. Once the input is detected, the microcontroller identifies the selected mode, updates the timer value, then controls the fan and the buzzer, and then it updates the display in real time. In the software, we will see how the embedded C programming variables are used for this system. Then let's talk about the output unit, which is a CLCD display. So CLCD display acts as the user interface for the system, which displays the operating modes, cooking time, then remaining time countdown, and system status like it is running, or it is paused, or it is stopped. Then microcontroller sends the control and data signals to CLCD to update the display whenever there is any change in the state. Then let's talk about the alarm unit, which consists of buzzer, which is used for alert purpose. Once the cooking time reaches 0, the microcontroller activates the buzzer to indicate that the operation is completed. So then let's talk about the block diagram. So here we can see that all the things now we have discussed are connected together to the microcontroller. All these components are interconnected, and the microcontroller acts as the central unit that synchronizes all the operations. This architecture ensures that efficient data flow and proper coordination between input, processing, and output units. So this is the PICSimLab simulator. So in PICSimLab simulator, we usually observe the working of all component as the keypad, display, fan, and buzzer. When we press any key, we see the real-time output. So we'll see that in the actual simulator.
So here on the left hand side you can see the project files in MPLAB. These include the source files and the header files required for this embedded application. In this project I have used if-else conditions to specify the key values. For example 3 for convection mode. Now I'll show the complete code where you can see how the logic is implemented step by step. The program continuously checks the flags and the input operations. Next I'll move to the header files. Here, all the declarations is done separating the header files from the source files to improve code readability. Now we'll move to PICSimLab.
So here I have used PICSimLab software to demonstrate the output. So here on the screen you can see the four modes we have assigned using code. So first one is micro mode, then grill mode, convection mode, and start mode. So now let's try the micro mode. So we are pressing 1 for micro mode, and you can see the power is 900 watt. Then we have to set the timer. So here we have setting the timer to 1 minute, and we'll use hash for assigning. Then we can see the fan is running, that means microwave oven is started. Then 4, 5, 6 are used for start, pause, and stop. So here we have paused the fan and then started it again. Then 6 is used for stopping the microwave. So here we'll try different mode. So we'll try the green mode by pressing 2, and then we'll again set the timer. So we'll set this value to 1 minute, and then hash is used for entering. So here again we can see the fan is running, that means microwave is on, and 4 is used for start, then 5 for pausing, and 6 for stop.
So that was all about our project microwave oven system. Thank you.